Hello, my name is Alonso Santiago, and I'll be showing this first part of the video from activity 3, that is the sun-powered motor control. And well, this is the first part. This is the code that we have developed in Teams. First of all, we have, as always, the configuration bits for PIC 16F877A. We have the libraries that we are going to use for this project. Have to define the frequency of the oscillator. In this case, we are going to use the 20 megahertz crystal. Then we have all the configuration of the ports. We can see that port B, C, and D are all outputs, and only RA1, that is going to be our input for the solar panel, is defined as 1 because it's an input. Then we are doing this in order to clear the buffers of all our ports. Then here are defined the pins of these LCD features we have here. And then we are defining our inputs, the driver for the motor in these pins. These codes are only to make our LCD work. And in here we have our PWM frequency and our timer prescaler. And well, here we have to define our ADC reading, our conversion analog digital. We define it as a float because we're going to be changing it. So we have to initialize it in 0 in order to make the conversion. So then here we have our line of code that will make our LCD work. These are the shift characters, the position LCD cursor, and more are only, all this is only for the functioning of the LCD. Well, then we have our configuration of the PWM. We have here selected our PWM mode, but in fact, the only ones that we're using are 0, CCP 1 and 0, and the one that is the 3 are the only ones that we use, that we're going to use actually, according to the datasheet. And then we have here the configuration for the PWM duty cycle in order to control the motor. So we have here an equations that is already given from the code that were given by the professor. And here we are only defining our PWM period as well. And well, the analog digital conversion of the solar panel. Here are the configurations of these features that we have done it according to the datasheet, and the THS configuration for the solar panel as well. And well, this is like only the showing of the amount of light that the solar panel is going to be receiving. And then we have our main code. We initialize our LCD, our ports, the PWM, the panel, and the conversions. And then we only go for this function. And well, we start this function actually, and then we set our inputs for the driver in order to make the motor move. And then here, all this line of code are only to display like an initial message that's a motor spirit control with light. There's like a presentation of the project, and then we have this while there's like an infinite loop in order to make the system work after all of that. Well, and that's all for the code. Now we're going to see how it works in Proteus. Here we have our simulation in Proteus, and well, I'm going to start it. And as we can see, the first message is displayed, motor speed control with light. In this case, we are using this potentiometer in order to simulate the solar panel because we can't use that component here in Proteus. So, well, first of all, we have to notice that the simulation is not going in real time. So it's going to be like a little bit slower in the simulation. But as we can see, the potentiometer, well, in this case, the solar panel is at 100%. So the motor is going to move very quickly at its maximum speed according to the nominal voltage, that is 5 volts. And if we decrease, as we decrease the light received in the solar panel, the motor is going to be moving slower and slower and slower. There we have it like at 50%, and we can see that it's considerable slower than it was at 100%. So if I keep on going down the light received, we're going to see that it's going to be slower. For example, that is at 20% and it's going really slow. But if I go to 10%, it's really, really slow compared, for example, to the 100%. We can see that if we meant all, the motor goes fast again. So with this, we can prove that our code and simulation are working correctly. So now it's time to see the physical implementation in real life. Thank you for your attention.